Welcome back again. This is going to be part number 2 of basically chapter about groups, context, and communicators and caching. We are going to continue from where we left off, was from, I think, from this sort of sentence. For this case, MPI World is a communicator of all MPI processes available for the computation. This communicator has the same value in all MPI processes. In an implementation of MPI where MPI processes can dynamically join an MPI execution, that's the dynamic process model. It may be the case that an MPI process starts an MPI computation without having access to all other MPI processes. In such situations, MPI World is a communicator incorporating all MPI processes with which the joining MPI process can immediately communicate. Therefore, MPI World may simultaneously represent disjoint groups in different MPI processes. Okay. Also, notice that MPI World cannot be deallocated during the lifetime of the MPI process. That's very, very important. And also, you can ask MPI Group to get the sort of associated group inside this MPI World communicator. Let's jump into the first section, which is about group management. So I think I have only one example here, MPI group. Yeah, group management. I have only one example here, but we're going to take a look at that example after we have seen a lot of these procedures or operations. Because I thought that communicators are more important than groups, so I only have one example for groups to basically show different aspects or different operations in group and group management. So this section describes the manipulation of MPI process groups, and these operations are all local. The first one is group accessor, which is MPI group size, similar to, you remember MPI size, right? MPI size and MPI rank to get the size of that communicator and to get the rank of that communicator. So we have also a similar one, MPI group size. So you're going to pass in as an input your group, that's a group handle, and then you're going to get as an output, you're going to get the size or the number of MPI processes in that group. So this is how the C binding looks like. So MPI group is going to be the group, and int star size. Notice that this is not an integer, it's an int star. MPI group rank, similar to what we had in MPI rank. This one you pass in your group, you get your rank of the calling MPI processing group, or MPI undefined. So if a process runs this basically procedure and the group that it passes, that process is not part of that group, it's going to get MPI undefined inside that rank. Okay. The next one on the line is MPI group translate ranks. So this sort of operation basically helps you to see the equivalent ranks in group 1 to see their equivalent ranks in group 2. So let's say I have processes 0, 1, 2 in MPI World, and I have the same processes in another group, group number 2, which is not equal to MPI World group. And let's say I want to know processes 0, 1, and 2 in the MPI World group. What is the respective rank in group number 2? Let's say processes 0, 1, and 2 in MPI World are members, like they have ranks of like 5, 7, and 12, for example, in group 2. So this is what MPI group translate does. You pass in the first group, you pass in the number of ranks or the number of elements in ranks 1 and rank 2, they have to be the same. And then you pass in the ranks, which is corresponding to these elements in group 1 or the processes in group 1. You pass in the group 2, all of these are inputs, and then what are you going to get from this operation is the rank 2, which is the array of corresponding ranks in group 2. And you can see that these are sort of int rank 2 array. So this is an array of integers. Also, this is an array of integers for rank 1. This function is important for determining the relative numbering of the same MPI processes in two different groups. This is what I said basically in MPI World group, for example, and group 2, a fictitious group. For instance, if one knows the ranks of certain MPI processes in the group of MPI World, one might want to know their ranks in a subset of that group. Yeah. This is the example that we had. MPI proc null is also a valid rank for input in MPI group translate ranks, which returns MPI proc null as the translated rank. Next one on the line is MPI group compare. So as you might have guessed, you pass in your group 1, you pass in group 2, and then it's gonna tell you, it's gonna compare those two groups, and it's gonna tell you the result. The result in this case is gonna be only 3 possible values. This is, by the way, how it looks. The result is an int star. The result is gonna be 3 possible values: MPI ident, or identical, results if the group members and group ordering are exactly the same in both groups. So if I have group 1, it has processes 0, 1, and 2. And I have group 2, it has processes 0, 1, and 2. Those processes are exactly the same. Their ranking, their ordering are also the same. So this means that MPI ident is going to be returned if I compare those two groups. MPI similar is that if the processes are the same, but the rank is different. So for example, let's say I have 0, 1, 2 as the ranks for those processes. And then in the other group, I have, for example, 1, 0, and 2. The ranking, the ordering of the ranks of those processes are different. And MPI unequal is basically neither of the two cases. If it's not identical and not similar, it means that they are unequal. Group constructors. So we're going to talk about these constructors now. Let's see this rationale. In what follows, there is no group duplication function analogous to MPI comdup defined later in this chapter. So you can duplicate a communicator, but you cannot duplicate a group. And the reason for that, or the rationale for that, is there is no need for a group duplicator. A group once created can have several references to it by making copies of the handle. The following constructors address the need for a subset and supersets of existing groups. Okay, so these are the constructors. MPI com group, you pass in a communicator. That's your input, and it's going to give you the group of processes. So this is what I was talking about earlier when we were talking about the intra-communicator and the world model with MPI com world. If you pass in MPI com world here, you get all the group of constituent processes which are in your MPI application. So you can see the communicator has the type of MPI com, and the group has the type of MPI group. And it's a star, so it's a pointer. MPI group union, so this is next one on the line. It's sort of in the category of group constructors, but I see this thing, group union, as an operation. I don't see it as a constructor, but you can also, because it also gives you a new group. So it is a constructor, but I would like to categorize it as a group operation. So you pass in group 1, you pass in group 2, and then you're going to get a new group, which is the union of these two groups. What is a union? It is these operations are similar to the operations that you can do, for example, in sets in mathematics. Like, for example, you have union. Union means that you have processes in group 1, processes in group A, and if they have intersection, if they have overlapping areas, it's going to be only counted once. So you're not going to have duplicates. So that is union. MPI group intersection, as the name suggests, again, this is going to be the processes which are shared between group 1 and group 2. It's going to be inside this new group now as an output handle. And MPI group difference is going to be, if you say group 1 and group 2, then it's going to be the difference. So it's going to be group 1 processes minus the processes which are at the intersection of group 1 and group 2. That is basically the definition of MPI group difference. So these are those operations that you can do. These are set-like operations. All elements, we already mentioned these. I don't want to read them again. This is union, intersection, and difference. But there is a very, very important thing here. Note that for these operations, the order of MPI processes in the output group is determined primarily by order in the first group. So if I have union, it means that all the processes in the first group, followed by all processes in the second group, but the ordering is going to be starting from group 1. Intersection, all elements in the first group that are also in the second group ordered as in the first group. Difference, all elements of the first group that are not in the second group, again, ordered as in the first group. So you see that it says, note that for those operations, the order of MPI processes in the output group is determined primarily by the order in the first group, if possible, and then, if necessary, by order in the second group, if necessary. Neither union. Why do we say if necessary? For example, if group 1 is something like MPI group empty, then it's necessary to basically go and see the rank in the second group, right? So neither union, this is super important, neither union nor intersection are commutative. They are associative, but they are not commutative. Why? Because if I have union group 1, group 2, and then I have union group 2, group 1, the final result of those groups, the final result of those processes are going to be exactly the same, but the ordering is not going to be the same, because always it takes the ordering starting from group 1. And if I have group 1, group 2, the ordering is going to start from group 1. But if I have union of group 2 and group 1, the ordering is going to start from group 2. So that is why it's not commutative. The same way, intersection is the same. Intersection is the same. So if I have intersection of group 1, group 2, it's going to be the processes which are basically shared between the two, or they are overlapping between the two, and the ranking is going to be taken from group 1. And if I have intersection group 2 and group 1, so group 2 comes first, then the ranking of those processes are going to be based on group 2. So that is why they are associative, but they are not commutative. And one thing which is super important is that MPI group difference is neither commutative nor associative. So if you write it on a piece of paper, for example, like you say A, B, and C, 3 groups of processes, and then try to basically have this, for commutative, you only need 2, A and B and A, to see whether the result is going to be the same. And then for associativeness, you have like A, B, C, and A, B, and C. So to check that, have a piece of paper and try those combinations and see why they like these two, union and intersection are associative, but they are not commutative, and why MPI group difference is neither commutative nor associative. Okay, the next one on the line is MPI group INCL, which is basically include. You pass in a group, you tell the number of elements, and you give their ranks, and then you're going to get a new groups. So this MPI group include basically takes a pre-existing group and then tries to include the ranks which are inside this group as a new group, which is going to be the new handle. So that's how it looks in C binding. The ranks are an array of integers. And this is exactly what I said. The function MPI group include creates a new group that consists of n MPI processes in group with ranks of rank 0 up the way to n-1. The MPI process with rank I in new group is the MPI process with ranks I in group. So each of the n elements of ranks must be a valid rank in group, and all elements must be distinct. So you cannot have repetitive elements, repetitive processes, or else the program is erroneous. Okay? If n equals 0, if you want to include basically 0 elements in your new in your new group, not communicator, the new group is going to be basically MPI group empty. It's not going to have any elements in it, right? So this function can, for instance, be used for reordering elements of a group. See also MPI group compare. Next one on the line is MPI group exclude, or EXCL. That is exactly sort of the cousin of the include one. You pass in a pre-existing group, and then you say from that pre-existing group, I want to exclude this number of processes, n number of processes, and the ranks of those n number of processes in this array of ranks. So this means that if I put n as 0, this means that I'm not going to exclude anything from that pre-existing group. So this means that new group is going to be exactly the same as group if I put n equals 0. Yeah, these things we already mentioned. MPI group range include. This is similar to include, but it gives you a flexibility to basically give ranges. And you give ranges as triplets. So it's a one-dimensional array of integer triplets. You see that in the definition. Ranges is a two-dimensional array with always the second argument is going to be 3 because we said we're going to pass in triplets. And what are the information in those triplets? You're going to pass in the first rank you want, you're going to pass in the last rank you want, and you're going to pass in the stride. It gives you more flexibility. You can use this also constructor as well. Same way that we have this range include, we're going to have range exclude as well. We're not going to go through this. We're going to see an example, and you're going to see how basically this range include basically works. But one thing which is super important is that we may have first element greater than last element, and stride can be also negative, but cannot be 0. So this is also super, super important. We don't care about the details now. We're going to see all these examples in group management. MPI group range exclude, it's exactly the cousin of range include. It basically excludes those processes and processes with those triplets information, first rank, last rank, and then the stride, and then it takes it out from the group. Again, the ranges is going to be a two-dimensional array which has sort of 3. Always it has 3. The second argument is going to be 3 because we have triplets. Advice to users: the range operations do not explicitly enumerate ranks and therefore are more scalable if implemented efficiently. Hence, we recommend MPI programmers to use them whenever possible, as high-quality implementations will take advantage of this fact. So we're not going to cover this one. I put an X here because this is MPI group from session pset. That is, we haven't talked about session model and process sets. So I'm not going to talk about this one. So we have group destructors, and I say all in one example, see MPI group management. This is exactly sort of this file here. Take a look at it, MPI group management. But before that, let's take a look at group destructors. When you are basically allocating resources, you also need to be responsible and, and free those resources after you have done your job with them. So MPI group free is basically sort of the destructor that you need to use. It's very simple. You got to pass in your group, and then this operation marks a group object for deallocation. The handle group is set to MPI group null by the call. So MPI group null, we already know that that's an invalid handle, right? So when you pass it to a free operation, it's going to be invalid after that point. Any ongoing operation using this call will complete normally. So there is no basically place to panic. After that, we're going to jump into communicators. But first, let's jump into this example. So these things are exactly the same as before, rank and size. And we have sort of this example for process numbers more than 8 processes, let's say. We have the world group, and then we query MPI com group, we query MPI com world, we pass in the world group to get all the processes inside that MPI com world. Also notice that this G size and G rank is basically group size and group rank, and I fill it with MPI group size and MPI group rank. I pass in the world group in both of them, and then I pass in the G size and G rank. And G size and G rank are going to be exactly the same as rank and size. And the reasons are obvious because we are basically passing here MPI com world, and here also we are using basically. So if you are using MPI com rank, it basically means that, let's say, behind the scenes, you are basically figuring out what is the underlying groups of these MPI com communicator or MPI com world, and then you ask from that group of processes with MPI with MPI group size and MPI group rank, and then you pass those results back to this rank and this size. But since these operations are so common for communicators, that is why we have a separate sort of operation for that. We're going to see that when we are talking about these communicators. Anyways, so G size and G rank are exactly the same as rank and size. And with in root process, we basically try to show the communicator size, and that is going to be size. Group size, you're going to see that this is these two numbers are going to be exactly the same. And then we also print the rank of root process. So now we want to create a new group. So we create a type of it first, MPI group, custom group. That's a customized group. We want to add the ranks of processes number 2 and process number 3. Ranks in world group to be included in custom group. So that is the constructor, MPI group include. We have seen this constructor earlier in the standard. So you pass in your pre-existing group, that is MPI, that is world group. You pass in the number of processes you want to add, 2 in this case. You pass in the ranks of those processes, process number 2, process number 3. And you pass in the handle of the group that you want to basically construct. And then you create new ranks because you want to know in that custom group, what is the rank of those processes? Because we know that their world group rank is 2 and 3, but they're going to be reordered in custom group, again, starting from 0 all the way to size -1. So we're going to have corresponding ranks in custom group. So that is why we use MPI group translate ranks. This also we have seen it in group management operations. So you pass in your pre-existing group, which is the world group. The number of processes is 2. The ranks is the process number 2 and 3. You pass in the new group, group 2, and then you want to ask from this basically operation, what is the processes that I have in custom group, what is the rank of those processes in custom group? So the processes 2 and 3 in world group, what is the equivalent process rank in custom group? It was so hard for me to basically formulate that sentence. And then finally, you see that one process which has nothing to do with these operations, you see that the group is process 2 and 3, but the root process also has information about that. And the root process is going to print the world ranks, which is going to be process 2 and process 3. Those are the ranks. And custom ranks are going to be 0 and 1 in the new custom group. We're going to see that what is the output of that. Now we want to see, for example, comparison of two groups. We have the result. That's going to be an integer. We said we have 3 possible results, MPI ident, and we had unequal, and we had similar. So we compare this world group with the custom group that we created with processes 2 and 3, and then we pass in the result in there, and then process number 0, or the root process, is going to basically print the result of that comparison. Of course, since the number of processes are different, so if you use, for example, 8 processes, this world group is going to have 8 processes, the custom group is going to have 2 processes, so it's going to be, of course, MPI unequal. Group operations, if you have group 1, group 2, let's say we have 4 processes, process number 0, 1, 2, and 3 in group number 1. In group number 2, we're going to have 3, 4, these are the ranks, processes 3, 4, 5, and 6. So you see that 3 is basically overlapping between the groups 1 and 2. So we're going to create those groups. We have allocated already sort of an MPI group here, group 1 and group 2. We pass an MPI group include world from world group. That's the pre-existing group. We want 4 processes. Whoops. I'm going to finish this example. This might be more than 25 minutes. I'm going to finish this example and go to the next episode. 24 minutes is already over. But let's finish this. I don't want to basically cripple this example. So we pass in group 1 ranks. These are the ranks that I want, 0, 1, 2, 3, and then we pass in group 1. We do the same thing for group 2, And then we want to do a union operation between those. And then that is why I create this union group as a new group, which is going to be the output of this MPI group union operation. We pass in group 1, group 2, and then we're going to get the union of these groups. Of course, the union is going to be 0, 1, 2, 3, no overlapping. 3 is counted once, and then 4 and 5 and 6. So it's going to have how many processes in that? It's going to have 4 and 4 is going to be 8. 1 overlapping minus 1 is going to be 7 processes in there. Size of the union group, you can ask for the size with MPI group size. You pass in the union group, and then you have this integer already allocated for that. And then for the ranks, you rank them. You know that the ranking system works always from 0 to size minus 1. You initialize that, and then you ask for the world ranks of those groups with this translate ranks. So you already know what is your ranks in the union group, but you want to know what is their corresponding rank of those processes in world group. So that is the purpose of this thing here. And then rank 0, or the root process, is going to basically print group 1, print group 2, those processes. And finally, it's going to print the union of the two groups. Yeah. Then we do the same thing for intersection. I'm not going to go through these because intersection and difference are exactly the same as union, but we have different basically groups allocated for them. So this is all the code corresponding to intersection part. And we have the same operation for difference between those two groups. I'm not going to go through that because, as I said, these operations are exactly the same. The next topic is group range operations. So we have a range group, and you remember that we were talking, when we were talking about this section, we said ranges, they have always the second argument is going to be 3 because we are working with triplets. And in this case, we have 2 basically. So this means that my first process is going to be 1, the last process is going to be 3, and the stride is going to be 1. So the first argument is going to give me processes 1, 2, and 3. And the second argument is going to give me processes 5, 6, and 7 because the stride is 1, right? So we're going to have this MPI group range include from world group with 2. 2 is basically the number of triplets that you have. We have 2 triplets. And ranges, of course, you need to provide that. And then you pass in the range group that you created earlier here. So how many processes are going to be in this range group? As I said, 1, 2, 3, 5, 6, and 7. So you're going to have 6 processes in there, right? Again, you allocate the rank for that, and then you try to basically query the ranks, the world ranks of those range group with group MPI group translate ranks. And then you ask the root process to basically print those information for you. We have a lot of freeing to do for all those custom groups that we created. We need to free those resources. That's why we have like a trillion of MPI group free here. We had custom group, group 1, group 2, union group, intersection group, difference group, and world group in the end. So let's just quit this and MPI CC, MPI group management, and MPI run with 5 processes. Of course, we cannot do that because we need to at least use 8 processes here. This is all the information. We already talked about that. We said we had 8 processes, communicator size is 8, group size is 8. As I said, G size is equal to size. And then this is the rank of the root, of course. And this is the first one when we wanted to have groups of processes 2 and 3. Their corresponding rank in custom group is 0 and 1. So 0 corresponds to process number 2 in world group, and 1 corresponds to process number 3 in world group. This is the comparison, the result of the comparison, which shows that world group is not is unequal or not equal to custom group. And this is the operation for union. We had processes 0, 1, 2, and 3. Group 2 had processes 3, 4, 5, and 6. And the union counts only 3 once. That's the overlapping process. It has 7 processes, as we already mentioned earlier. This is the result of intersection. You know that intersection, the only overlapping process is process number 3. And the result of difference is, of course, processes in group 1 minus the intersection that they have in group 2, which is minus process 3, which is going to be remaining of 0 and 1 and 2 processes. And then the final thing is the range group. As I said, we had processes 1, 2, 3 with a stride of 1, that is 1, 2, and 3. And then we had processes 5 through processes 0 with a stride of 1, that is 5 and 6 and 7. Again, we already mentioned that we have 6 processes here, 1, 2, 3, 5, 6, and 7. Okay, so we're going to continue. This example is finished. We're going to continue in the next part.